So I recently delivered this session a few days back in my in an open infosys community, which is known by the name of SegFault. I started SegFault a few months ago, precisely in the month of January, and since then we are having monthly meetups, which are free for all. Now, this session was quite a good one because we covered a lot of things, and it was again essential from the point of view that if you are, going for the OSCP or preparing for the OSCP, there's a module for exploit development on Linux, and this would serve as a base. So many people requested me to upload the session if we had recorded, but since that was full day session and it is really kind of boring to just wait and watch a around 10-hour long video. Yeah, that was around 5 or 6 hours, but again, in which most of the time people were asking questions, interacting instead of just focusing only on the main concepts of the session. Now let's start. So the title of the training is Exploit Development under Linux, and my name is Himanshu Khokar. I am a freelance information security trainer. I currently work at City Security Solutions, and as you can see, Mr. Dan, again, my interest is in low-level topics such as exploit development, malware analysis, reverse engineering, system programming, rootkits, things like that. If you want to follow me on Twitter, you can follow me on Twitter. This is the link. And if you want to connect with me on LinkedIn, I provided the link to my profile, so you can just go and say hi, connect with me. Now let's start. So the agenda for the whole session was buffer overflow exploitation, and since we already had a session on buffer overflow on Windows, which I am planning to record and upload, but again, we had an assembly section in that tutorial for the sake of people who don't know assembly language and who are new to even exploit development. But again, there were some new people, and I thought it's better to start with assembly language, just a brief intro. So if you are not familiar with assembly language, it would be a little bit difficult without knowing what we are doing. Now the second topic was shellcoding on Linux, in which we review how to write basic shellcodes, what are shellcodes. Now this topic is very limited in the context of this session because this was not the main topic, and we wrote shellcodes just for the sake of demonstrating that we can execute arbitrary code. Once we get arbitrary code execution, we move to using payloads from MSF Venom so that we can have bind shell, reverse shell payloads. Now then after that we discussed memory corruption vulnerabilities, what memory corruption vulnerabilities are, what are different subclasses under this class of vulnerabilities, and what our focus is. I gave just a little intro about different subclasses which were not the focus of the agenda, but again, then we moved to in-memory view of process, in which I explained what was how a process is represented in memory. There are different sections: .text section, .code, then there's a BSS section, then stack, heap, how stack grows, how heap grows, what are the various reasons for growing or modification of the heap and stack. Then once we had the basics covered, we moved to Stack Overflow vulnerabilities. Now in the Stack Overflow vulnerabilities, we wrote very simple, just for the purpose of learning, some very simple programs, vulnerable programs, and then we started with the exploitation of Stack Overflow vulnerabilities. Once we were able to obtain arbitrary code execution, once you were able to execute or injected code inside the process memory, then we discussed NX memory protection, what the NX memory protection is, how it affects exploitation, what it offers, what it lacks in. Then we discussed how we can perform return to Libc style attacks and obtain shell on the system. Now, the last thing which I discussed was that using return to Libc, we can not only just bypass the NX memory protection, we can also execute shell code even when there's not enough room, such as if there are 8 bytes or 10 bytes, there's not much room for any sensible code execution or whatever, and you cannot do anything useful in around 10 bytes of shell code. So we discussed how we can leverage return to Libc attacks when we don't have enough memory for the shell code. And then the lecture was concluded with the final road ahead movement, in which we discussed a little bit of return oriented programming, how we can use rope. So let's start. Now let's start with the assembly language. Now, assembly language is a non-portable programming language. It was used in kind of, I would say, ancient ages of programming. But again, it is non-portable, and non-portable is in the sense that when we say something, some programming language is portable, we mean that it is portable both on different architectures as well as on different operating systems. Now, our focus is the Intel x86 architecture, which is 32-bit microprocessors. And now, if you write programs, assembly language programs for the Intel 32-bit microprocessor, they won't run on any other processor families that does not support the Intel x86 format or the Intel x86 instructions, such as mobile devices, ARM, Spark, PowerPC architecture, those things. Then assembly language is practically useless for anything if you want to consider using assembly language for writing full-blown applications. We generally use assembly language as small fragments inside our high-level programs, such as the programs written in C or C++, where we can embed particular assembly. We can use inline assembly, and that way it is generally used, because it's really tedious to perform anything in the assembly language. Then now you may ask, if it is kind of useless for anything good or big, why should we learn it? You should learn it if you want to learn how microprocessor works, how it accesses memory, how it works, how it actually works, how it performs operations, and those things. The focus is again the 32-bit Intel architecture. Now, while talking about discussing microprocessor architecture, there are lots and lots of concepts, but we will be discussing only the relevant details here. Now, for those who are completely new to the assembly language, microprocessors offer some internal storage for the sake of processing. Now, these are known as registers. Registers are internal storage for the microprocessors, and since they are built into the microprocessor, they offer the fastest operations. Now, you can perform addition, subtraction, multiply, divide, moving inside and outside of registers. Since they are built inside the microprocessor itself, they are the fastest. Then we have cache, which is kind of much slower than the registers. Then we have main memory, which is around hundreds of times slower. It takes around hundreds of cycles of CPU, something like that. So yes, but we have a limited number of registers, and in the Intel x86 we have 8 general purpose registers. Now, we have general purpose registers, we have segment registers, we have MMX registers, we have XMM registers, YMM registers, then we have control registers, we have debug registers. So we have very kind of huge variety of registers, but since we are at the very basic level, so we will be discussing only what is needed. Now, moving on to the general purpose registers. The general purpose registers are the registers which are, as the name says, used for kind of general purpose. Now, we have 8 of them, EAX, EBX, ECX, EDX, ESI, EDI, EBP, and ESP. Now the first four registers are generally used in the arithmetic operations, while ESI and EDI are especially used in string operations. The ESI stands for Extended String Index, and the EDI stands for Extended Destination Index. So ESI and EDI are generally are implied registers or operands in the case of string operations when we are performing operation on strings, such as copying a string or loading a string into memory or things like that. Then we have stack management registers. Now EBP is not such hardcore stack management register, but again it's used to save the value of ESP when entering a function stack or entering a subroutine stack when the subroutine of the function is called inside memory, so that member variables or local variables, the better word is local variables, or the local variables inside the function can be referenced by EBP. We can do that with ESP, but again if there are some operations that need moving of ESP, then it becomes kind of hard to manage all that stuff up and down and again referencing. So it's generally a practice to move ESP into EBP when we are moving inside a function and then reference local variables from the EBP. Then once the function has executed, we pop the value back into ESP so that normal functioning of the process can go on. Then these general purpose registers are word sized, and the word is, now there are different meanings of word. Sometimes it's 2 bytes, in some places it's 4 bytes. What I'm saying word is, it is the native word size of the machine, and on the 32-bit machines it is 32-bit in size. So we can say that these registers are 32-bit in size. Now you can reference their, instead of just using whole 32 bits at the same time or at a time, what you can do is you can access 16 bits or even individual 8 bits at a time. To access the lower 16 bits of these registers, you, instead of using EAX, for example, let's talk about EAX. The EAX is a 32-bit register, but if you want to access the lower 16 bits of EAX, you use the word AX. The E stands for extended. Fine. So, same goes with EBX, ECX, EDX. You can remove the E and then you get the lower 16 bits of the 32-bit register. Now if you want to then access lower 8 or upper 8 bits of the lower 16 bits of the 32-bit register, then you can use AL for the lowermost 8 bits and AH, which stands for A high, and AL stands for A low. Then by using the name AH, you can use the upper 8 bits of the lower 16 bits of the EX register. Now EBX, ECX, EDX can be used that way. ESI and ED, the remaining 4 registers cannot be used that way. The remaining 4 registers can be just use 16 bits. Now you can use ESI and EDI, I don't know, probably ESI in the way, SIL for SI low, but again we don't need to consider that for the moment, because we will be dealing only with EX, EBX, ECX, EDX and ESP for the rest of this whole presentation. Now we have 6 segment registers. CS stands for code segment, DS for data segment, SS for stack segment. ES stands for extra segment. FS and GS are kind of addition to the whole segment registers. So those are just extra segment registers. Now these segment registers were primarily used in the segmented memory model, which was prevalent in the era of 16-bit CPUs, where we had a 20-bit address and the 16-bit address bus and things like that. So that was kind of complicated, and since we don't really use the segmented memory model these days, we don't really need to consider them. In some cases, segment registers are used. Okay, so now moving on. Now we have EIP register, which is the extended instruction pointer register, and it holds the address of the next instruction that will get executed. So when instructions, the way instructions are taken and executed from the process is that the program is loaded in the main memory and the EIP points to the next instruction that will be taken from the main memory and then will be decoded and then executed. So essentially when you are debugging a program or things like that, you can see where the EIP is, and if you just step one instruction, then that instruction gets executed. So we'll see this when we will be using the debugger. For now, it's just since EIP is the instruction that points to the next instruction to be executed, all you would want to do is to control the EIP so that you can redirect the execution control to where you have positioned your shellcode. Then we have the eFlags register, which is the extended flags register, and it is the register that holds various flags about the states of operation, such that whether the last arithmetic instruction resulted in 0 or it was a signed operation, or probably there were bits which set the parity flag. The eFlags register is 32-bit in size, and we are just not really looking into that detail. For more information, you can refer to the Intel manual where they refer and explain everything in the eFlags register. For the floating mode operation, XMM registers are used. There are 18 number and 64-bit in size. Then for extended floating point calculations, XMM registers are used. Those are 128-bit in size and around 18 number, if I'm not wrong. Then if the floating point operations are particularly interesting because they have their own stack, they have their own instructions, they have their own flags register, their own exceptions, but this is not the part of this talk, so let's just skip for that now. Then we are moving to the end of the basic concepts. Then there are two ways to write the Intel assembly language instructions. One is the Intel syntax and the another is AT&T syntax. Now the GNU tool chain generally uses the AT&T syntax by default, but you can kind of force them, or you can specify that you want to use the Intel syntax. In this session or in this video, we will be using the Intel syntax, and we will be using NASM as the assembler to assemble our programs. To link our programs, we will be using the GNU linker, which is the LD binary. Now instructions can be in the form of mnemonic, which does not take any arguments. Then we have mnemonic and source, which take only one argument or one operand. Then we have mnemonic with 2 operands, and then we have mnemonic with 3 operands. Now in the case when there are 2 or more operands, then the first operand is always the destination operand, and we are talking about the Intel syntax. From now everything will be for the Intel syntax. The operands must be the same size, and the result of the instructions, such as where the destination and source are used as operands, destination equals to destination and source. Those are both operated kind of like if we have add ex comma evx, then ex will contain the value of ex plus ebx, while ebx or the source is always remain unchanged. Now let's talk about shellcoding a little bit. Shellcoding. A shellcode is a piece of code or a payload in the exploit that runs in the context of a process, which is usually a part of the exploit, or result of exploit, whatever you want to say. Then shellcodes can be used for almost anything. You can read files, write to files, open connections, execute code, whatever. Shellcode is just a program, so you can do almost anything with the shellcode. But since we have a very limited space in the context of the buffer or the program exploiting, we usually try to obtain a shell or reverse shell so that we can then remove that restriction of the size and can perform anything. In the current context of the session, we will be writing very primitive shell codes just to use as the proof of concept to demonstrate arbitrary code execution, and later may use payloads generated by the Metasploit to bind shell or do any other fancy stuff. Now, there are some things that you need to remember when talking about shellcodes. Shellcodes are written in assembly language for the reason to save the space and make it as compact as possible. What this means is that if you are using any compiled language such as C, C++, or things like that, when you write even a very minimal piece of code, the compiler adds a whole lot of code. In the case of very little programs such as this kind of printing hello or things like that, the compiler adds much more code than even you wrote. So since we have space available in the magnitude of bytes, like 10 bytes, 20, 30, 40, probably 800 bytes, that is kind of stupid to just waste it like that. So but if you write in assembly language, you will obtain the exact same instructions and nothing else. So that is why we use assembly language in shell coding. Now, since we have since we have space restrictions, shell codes must be as small as possible. Probably, even if we have large space around 500 or 2000 bytes, we should generally try to, not just go for the whole space available. We should just use whatever is just enough for us. Then, apart from the limited amount of space, we have another hurdle, which are bad characters. Now, bad characters are the characters which lead to the termination of copying or taking input, such as you are using the function string copy. Now, string copy will terminate copying the string when it encounters null bytes. So, if your shellcode has null bytes in it, then at the point where it has null bytes, after that, the remaining shellcode will not be copied, and you are left with half the shellcode or incomplete shellcode, which is, not really useful. So, we should take care of the bad characters. Now, nulls are not the only bad characters or the universal bad characters. Different functions have different bad characters, and that's why you should enumerate when you have the chance to make sure you have figured out all the bad characters in the application, and then in your shellcode, and then replace them. Okay, so let's start with shell coding on Linux. The first thing we will be writing is the exit shellcode, or the shellcode which just exits, but with error code 1 or the exit status 1, so that we can see if our application is exiting with return code 0, we are getting our shellcode executed. Now, you can see that we have exited with the exit code 1, and we can use a utility called strace, which traces the system calls, and verify that it is returning with exit 1. See here. So now we can just have a look about the assembly language. So those who are unfamiliar with the assembly language, the text section, this signifies that the remaining or the following lines are the part of the text section, and the text section is the section which contains the executable code inside a binary. Now we define a global variable start so that the linker can find it and make it the entry point of the executable. Now entry point is the point from which the actual execution of the binary starts. So in this case, it will be start. Then then we have put the start label, and we have moved the value 1 in EAX, which is the system call number for exit in Linux and the EBX contains the argument which is 1, since we are going to exit with 1, and so we have moved 1 into the EBX. Then we interrupt to the kernel to make the system call, and we just wait. Now if we just execute this thing, we see that we got the exit code 1, but there is a little problem with this thing. Now since, if you remember, I said that with instructions the operands must be the same size. Here EX is of 32 bits, and since 1 can fit in 1 bit also, so the remaining 31 bits will be 0. Same goes for the second line. So you can see we will be having null bytes. Now we will be using the object dump to show us the opcodes and the disassembly of the text section or of the binary. Since this binary just contains the text section and nothing else for that matter, it doesn't really matter. If we will just disassemble the whole binary and use the -m intel switch so that it displays disassembly in the intel format. So as you can see, it has exactly the same instruction that we put in our program, but okay, let's just have a look at what the object dump says. The first column, these are the virtual addresses where this, so you can see that this the start label has the virtual address of 08048060. Now keep in mind that these are the hex, and even the first instruction also has the same address. Labels are at the same address, or we can say that the labels do not take any space, but they are just for kind of bookkeeping kind of things that you can just refer to that location with that name. Now at this location we have move EX. The second column or this part is the opcodes or the binary sequence in hex of this instruction. So you can see we have P8, which is move EX or move into EX. Then we have 4 bytes, and now you will note that this is written in reverse because it is 1 and not 1 followed by 6 zeros. This is because of the little endian architecture of the Intel. You can read about the endianness on the Wikipedia, which is explained in proper depth. Then the same goes for the second instruction. We have BB followed by 1 and 6 zeros, and then CD18. Now if you remember, we said that shellcode must be as small as possible, so we need to eliminate this thing. Now let us eliminate this thing with let us rewrite this thing. Instead of moving 1 into 32-bit register, let's just move into lower 8 bits and lower 8 bits of PX as well. And let's disassemble it again. So you can see that now we have gotten rid of these nulls, plus we have decreased the size of our shellcode to just 6 bytes instead of 12 bytes. Now we have removed the null characters as well as shortened the size, which is a good thing. Then there is again a little problem with this shellcode, and that is when this will run in the memory of a process, we will not know, or we are not sure of what will be the value of EAX at that point. So if it is anything other than 0, then it is going to be problematic for us, as we will not be able to call the exit system call. So for that we need to make sure that the EX and the EBX registers are the same. So let's just go EX and EX, and this zeroes out a register. Anything exclusively odd with itself results in 0, and let's just move EBX and this thing. Let's assemble it again, and we got exit 1 working fine, and see this. So we have added 4 bytes, but now we have made sure that even if it is inside the memory and whatever be the value of EX or EBX, we will be executing the exit system call with status 1. Now once you have taken this thing, once you have obtained the opcodes, what you need to do is you need to take these and put it in the test program. So the test program we are considering is this. So this is a test program which we have said we have declared a constant unsigned character shellcode, and then in the main program we have just declared a function pointer which points to nowhere at this position, and in this line we are printing the shellcode length. In this line we are assigning the location of our shellcode, which is basically all the opcodes taken together and written next to each other, and then we are jumping to that location and calling it. Now if you see at the end of it we are returning 0. So if our shellcode gets executed, we will return 1, but we have not yet done that. So to do that we can either do okay. So I have taken this script from this command line foo website, which automates this task of taking or extracting the opcodes from the object dump output and arranging them in a nice to use C style character array or character string. So but since I'm using the Z shell and this post is on bash shell, I found a comment someone made, Akshay, Krishna and R made about the Z shell users. So I took this and I used this thing. So you can take this. Now I'm using the get opcode and exit 1, and see I got 31C0 31dB B001 B3, 31C0 31dB B0 this thing. It is exactly the same. So let's just copy and paste it here like this. Now let's just compile it and execute it. Test shellcode. And we see that we exited with the return code 1. To verify that the exit syscall was invoked or called, let's just run it with test shellcode, and we can see up to the right we have exit 1, which was, if we scroll up here. So yes, our shellcode gets executed. Now if we compile it with this without the exec stack and test shellcode, oh, actually works fine. Okay, so we can see that our shell code gets executed as we try to make it. Now you can use this shell code in your test program and see. So this was basically how we just use this. How just we write shell code in assembly, extract its opcodes, and then use it as a shell code or payload. Now let's write another payload which will print a hello world on a screen. For that, I have already written that thing. So now let's just see what this is. And okay, let's start with again a little description about this program. Now it uses a technique which is a jump call pop technique, and which essentially works like this. So we start with star, the label, and we perform something, then we jump to a label here, here, then we call this label so that we can obtain the address of this string dynamically. Now you might ask why. So let's just first write a shell code which is just a plain simple assembly language program for printing hello world on the screen. Name hello.c. Okay, so here we can see that we have printed hello world, and if we see the exit status, it was 0. Now let's move to the program and have a look. So we have a data section, and in the data section we have a string which needs to get printed on the screen. The system call number for the write system call is 4, and let's see what parameters it takes meant to write. So it takes 3 parameters. The first one is the file descriptor, in which it has to write. On Linux we have 3 by default file descriptors, which is the 0 is for standard input, 1 is for standard output, and 2 is for standard error. And since we are writing on the standard output, we are using the value 1. So the system call number, which is 4 for write, will go into EX. The first argument will go into EBX, second will go into ECX, and the third will go into count. So let's see. The first argument is the file descriptor. The second argument is the pointer to buffer from where it will start printing the bytes on the screen, and the third parameter is the number of bytes it needs to print. Okay, so let's say we are printing on the standard output. Now this instruction does, what this instruction does is to take the address of the string, which is hello world, which is labeled by the label string, into ECX, which will be the address of the buffer, which is the second parameter to the right system call. Then, since there are 12 characters, 5 hello, 5 world, 1 space, and 1 new line, total 12 characters, we move into EDX and we interrupt. Then after we have done the writing, we just move 1 into EX for the exit system call, and in this example we are exiting with 0, so we have moved 0 into the EBX. Okay, now since we can see that this works fine, let's see object dump -t hello. Now you can see that what this number is. This number is the address of the string hello world. So this is the location of the hello world string. But in the case of shell codes, we cannot rely on hard-coded addresses, because we don't know if we load this shell code into a process memory, what will lie at that location. And if it is anything other than hello world, then it's an unsuccessful shellcode, because it is not doing what it is written to do. So to achieve that, we need to make it position independent shellcode. And to make it position independent, also you can see that there are plenty of zeros, plenty of nulls in this whole assembly language program. So let's first decrease the size and then make it position independent. Now to make it position independent, we need to delete this, because we cannot have data section. All we have is code, and yeah, let's write it again, everything. Okay, so let's zero out the registers, EX, move EBX, EX, so that we make it null, and move EDX, EBX, so EDX also null. Add AL4, increment BL, jump. Okay, so the technique, which is the jump call pop technique, what it is that we jump to a location which is kind of much ahead of the current execution location, and we call back. Now you will see the reason in a moment, but just follow this. Okay, so what this instruction does is, how this will do, first we clear out EX, EBX and EDX. We don't need to clear out ECX, because that will be filled with a 32-bit value by itself when we pop the location of the string inside it. So yes, so even if it contains any other data, that won't give us any problem. Then we add 4 into AL, effectively making it 4, and we increment the BL, effectively making it 1, the EBX register. Then we jump to this label. What this label does is it calls this label, and now when we call a function or any other instruction, the address of the instruction just below the call, which is this string in this case, gets pushed on the stack. And when we are in this label piche, what we are doing is we are popping the address of the instruction which was pushed by the call instruction into ECX, effectively taking the address in ECX. Then we are moving 12 into the DL, and we are just then calling the kernel or invoking the system call, and then we simply move ahead and call the exit. Now let's just see if this works. Assemble, hello, hello, works fine. Okay, works fine. Object dump, see, there are no nulls and there is no hardcore address. Yep, that's great. Now let's get this and try to use this in our test program. Test.c, compiled, test C. So it executes fine. Now let us test this in the GDB -q and the program name. Yeah, let's just first test the program, our assembly language program. Now I'm using the GDB Jeff, which is very good at displaying information, plus it has some other commands. You can look for GDB Jeff, and it's very simple to use. It presents information in a very much more informative way, so you don't have to write instructions or GDB commands to see. Now you can just take it, clone it from the GitHub repo and use it. If you just want to do it via the installation script, just run this command, or you can just do all of that manually. Then now moving on to this thing, let's set a breakpoint on the start label, and let's run this program. So we see we have this XOR EX, EX, EBX. Now at the initialization of a program, as you can see here, that these are already set to 0. So let's just step I. Okay. So the next instruction is add AL4. Currently EX is set to 0. Now if we step I, or SI for short, see EX is 4. Now increment BL, and it will be EBX set to 1, which is what we wanted. Now we have set first two parameters of the right system call. Now if we press SI, we will jump to the AGE label, and what, if you remember, it does is the first instruction is called the piche label, and the next thing after that is the R string. Now as you can see, this is the instruction and this is the address of the instruction. Then from this location we have our string. Well, you cannot see this because the debugger has disassembled those bytes, individual bytes, and presented them as the instructions. So what we can do is, oh sorry, this is the piche. So yeah, let's just SI. And now what I said earlier, that was that it will push the string on the stack, and here it is. Now if we scroll back and see, there was nothing on the stack, but now it has pushed the string on the stack. The remaining stack is the same. As you can see, the top is value is 1, then this is the location of the program. See, this is the 1, this is location of the program. Okay, let's move. Now the ECX is supposed to contain the memory address of the string which needs to get printed. So let's si pop the value in ECX, and you see we have this string. So let's just examine the string at this location. We see hello world and new line. Great. Now let's si move 12 into edx and int, and we can see that hello world was printed. Now we are moving to exit. Here you can see that ex now contains the C or 12. Now ex will contain the return status of the last system call. So the right system call returns the number of bytes it printed, and since that was 12, so ex now contains 12. So let's just si, and since 12 fits in the lower 8 bits, we can just override the lower 8 bits with 1 and get ahead. So si now ex contains 1, decrement PL so that PL contains 0. So our exit system call is set up, exit with value 0, and if we si, you will notice that the program has exited. The process exited normally. Great. So this was how the shellcode worked. Now let us look at in the environment of a process or another program running. So since there was test running, so let's just use test shellcode and break main run disassemble. So this is the code for the main function. Now you see that this is called ex. Since we used a function pointer and the addresses were calculated at runtime, so the address, this was the value which was put into this location on the stack, and from stack it took this value and put it in ex. So let's just breakpoint on break main plus, let's say 35, let's say here, and we will see what this location contains. Main plus 35. Okay. Okay, we deleted the third breakpoint because that was at the same location at the 2. Now to continue, press C, enter. So we are at this location. Now let us see what this contains, and let's say 10 instructions. Okay, so this is our shellcode, if you remember it. So let's just si, okay, and now it is si, ex, and ex contains this value which we just disassembled and saw that it contains a shellcode. So si, and you can see EIP is this shellcode, and here is the location or is the character buffer in which we stored our shellcode. And if we just continue, we see hello world, and the process exited normally. So this is just the basics of shell coding, and this was shown to use that this was just taught so that we can use these shell codes what we wrote and try to execute them in the vulnerable programs. Then once we have confirmed that we can execute our injected code or arbitrary code, then we can use any other shell code if the space permits or things like that. So this was the first session, and to be honest, this is the first ever recording of a video which I am doing, so it will not be up to the quality, but again, now I broke the session into 2 parts because it was a little bit too long. Now the first part is this, where we understand how to do shell codes, how to write shell codes, how to analyze them in debugger. In the second part, we will be moving on to exploiting buffer overflows, understanding what buffer overflows are, how they actually work, how to exploit them. And then in the third part, we will be looking at how to perform return to libc attacks. So I have broken down this whole session into 3 videos. If you like the video, please press the like button, and you can subscribe to the channel so that you will be watching all the other session videos which I have done previously. I'll be making sure to create videos and upload them. Then I'm planning to regularly upload contents once or twice per week is what I planned for now. And apart from the sessions, there will be lots of other topics which I'll be covering, which includes reverse engineering, exploit development on Windows, Linux, malware analysis. Then we have some web application exploitation. So yeah, it will be very beneficial for you if you subscribe, and we'll meet you in the next part. Thank you very much.